Hello everyone, welcome to another live stream session. Inertia 2020 seminar September still ongoing. We have a little bit of packet loss today. It seems around 60%, so it's not that bad. Should be improving throughout the night. But if it doesn't, we have the video scheduled up on YouTube where we can forward you there for the seminar itself. Meanwhile, let's try play a few demos from Forever Demoparty, which is a small demo party in Slovakia that also got cancelled due to COVID, following the theme that we've been doing throughout these last few weeks of doing some demo shows of parties that got cancelled due to COVID. Today we're going to focus on Forever. So the first demo that I have to show you is Pond Life by Hoy Program and Raw Ars. It got first place at Forever Party 2001. It's the second year that Forever was held. It was already held in 2000. So yeah, let's take a look at the demo, and hopefully the packet loss will improve throughout the demo show so we can have a more stable seminar session. Anyways, be right back. Anyways, this was the mega demo. Pond Life won the Forever 2001. Let's move on to another demo because this is like 16 minutes long. So other demo we had lined up is Laya by 3SC. It got third place at Forever 2002. And this is a demo that won Alter Ego by Oikogram. Only OI program makes it possible. Next time we have lined up to watch today is Heart Fixer. It is for the C16. It's a version of the Commodore 64. The C16 plus 4. It won the Wild Combo in Forever 2003. Still have 5 minutes left, but the next demo I have queued up is like 15 minutes long, so maybe we should try something else. Hello, Brilliant Games, welcome, welcome. Welcome from Texas. Let's play Polymatrix demo, something for Atari. It's only 2 minutes long, that sounds legit. There was an Atari demo. Next up, some Spectrum love from 8-bit. And then we'll start the seminar. I'm gonna have to cut this demo short because it is 9 o'clock at least in Lisbon, so it's time to get the seminar rolling. Thank you very much for Soul of Hysteria for putting it together. I'm gonna switch to webcam so I can change my desktop stuff. The music will suddenly stop, which is completely normal, like this, and I'm gonna load up the video. So thank you everybody who showed up. The seminar was supposed to be about coding for the ZX Next, but Soul kind of turned it into his journey through programming for the Commodore for the ZX Spectrum, and I think it's just as interesting. So I think it's awesome. Let's take a look at that. If VLC would load. And now rewind, because you're gonna miss the important message in the beginning. Okay, so Soul, if you could post the link there for the Premiere as well, since we're suffering packet losses. If you want to check this video on Premiere on YouTube without these stutterings, please check it and then be here back for the Q&A after this for this session. So we'll post the link on the YouTube, on the Twitch chat, hopefully. So let's get the ball rolling. Please enjoy the seminar of, what was the official name? My Speccy Journey from 48K to the Next.
Hi, I am Jari Komppa, also known as Sol, and I'm here to talk about some ZX Spectrum stuff. This presentation originally started as talk about the Spectrum Next, but it turned into my personal ZX Spectrum journey, so you will hear some history of how the ZX Spectrum Next came to be and what it was built on. But first, a bit about my history. In the 90s I was in demo group Hysteria, and we made a couple of demos, which the old PC demo scene people might recognize. I was more in a supporting role than in design, graphics or code back then. I made tools and ran the BBS and stuff like that. In 95 I did code my first real demo, but it was unreleased at the time because we didn't feel it was good enough or something. It was released much later on when I found it and figured that what the heck. Then after 96 we formed a new demo group called Trauma, and I was more active in the design and coding. And we made a bunch of demos, some of which were rather successful in the assembly demo party. And I was also a part of a music group called D, and we released a bunch of music discs. And I spent a rather long time building a music disc interface called Horse, and we released a bunch of music discs using it. It had a HTML-like renderer and multitasking and all sorts of stuff. It was rather crazy. Anyway, it just meant that I was a better programmer by then, and I took more active part in coding the demos and designing them. Trauma released Mind Trap, Gateways, Traumatic, stuff I worked together when I was bored, and Lineage, all on assembly demo parties. Then I've been an active part of text mode demo competitions, so much so that you could say that I basically made the whole text mode demo scene. I ran the TMDC competition for 10 years, and after that I took part in several of the later ones that I didn't organize and won most of the time. And finally, I have this tradition of making a demo every new year as part of the demo group Thought. Thought is like a B group for demo sceners. Many of the members have a more serious demo group, and then when they just want to do something simple and release it, they release it under the Thought label. But the New Year demos have become a bit complicated sometimes. And outside of the demo releases, you may know me from the Atanua Logic Simulator, which I made as my final project Atel for a few years, but everybody said that they loved it and would have loved to have something like that when they were learning digital logic, but nobody wanted to pay for it. Then I have probably the biggest hobby project that I've ever made is the So Loud audio engine, which is a pretty decent audio engine for games, which started as from my frustration with SDL Mixer, and that it didn't do something that I wanted it to do, so I figured that how hard can that be, and then I've been working on that on and off for, I don't know, over 7 years. Many of you probably have also sometimes visited my website, which contains tons of stuff that I've written more or less because somebody's asked about something, and then I figured that it's easier to just write a web page than keep explaining the same thing over and over again. But let's start talking about the Spectrum. I was born in 1975, so I was 7 and in school learning to read when the ZX Spectrum was released in 1982. I remember being in the living room having a fever and watching my siblings try the first things out with the Spectrum. I can't remember if we used it much as a programming device. Probably we learned about how to write some basic programs, but I can't remember any real projects with it. I know that many people have written games with the 48K Spectrum Basic, but I don't think we ever did. We did play a lot of games though. I remember that my father had to get replacement membranes for it because we had hit the space key so many times that the membrane had broken. Then in 2015 I turned 40 and There were some people who were interested in retro programming. Friends were doing things with Commodore 64 and stuff like that, and I just got inspired that what if I take that old Spectrum and do something with it? Not with BASIC, but to do something in machine code and do something real with it. So I went to my parents' place, found the old Speccy, brought it back home and nursed it to life. So, to look at the internals of the 48K Spectrum. The key thing to know about the Spectrum is that it is a cheap device. Basically everything that it has been driven by the price, how to make something usable as cheaply as possible. The whole thing is built around the Zilog Z80A CPU running at 3.5 MHz, knowing that most of the instructions take something like 4 clock cycles or T states as the Zilog terminology goes, means that it's running at roughly 1 MIPS. There's no barrel shifter, there's no multiplication, there's no divide, so it isn't the fastest thing out there. It's also an 8-bit CPU, so the memory space that it can see is 64K. More often than not the Spectrums came not with the Zilog part, but with some cheap code, like the NEC part. The Spectrum contains 16 kilobytes of ROM, 48 kilobytes of RAM. 16 kilobytes of the RAM is called contended because it is shared with the ULA or the graphics chip, so to say, and 32K is uncontended. If you are more familiar with the Amiga terminology, the 16K could be called chip memory and the rest would be fast. There's also a piezo speaker as the audio output. Video goes out from the TV output part. You would plug this into a TV and then choose a channel to see the image. In modern use, there's a rather easy hack to bypass the TV output and just output a composite signal. And the heart of the device is the ULA chip. The ULA comes from the words unassigned logic array or something of that sort. A modern part that's similar to the ULA would be an FPGA. So instead of making a real chip, the Spectrum was made with a programmable logic chip. There's also 2 audio ports, but those are for loading programs and saving programs to tape. As you can see, there are no joystick ports, there's no reset switch. The ULA can output just one graphics mode. It's a 256 by 192 bitmap, which is not linear because of reasons. ULA needs more memory bandwidth than would be possible if the bitmap was linear or something like this. It doesn't really matter what the reason for the scrambled order of the bitmap is. It's just a hassle for the programmers. In addition to the bitmap, there's a 32 by 24 byte linear color map, which describes what 2 colors each of the 8 by 8 cells on the screen may have. So you have a bitmap, which means you have just one of 2 colors. The color map just says which those 2 colors can be. The Spectrum has a 15 color palette, mainly just primary colors and bright versions of them. And since the brightness is controlled by 1 bit, it means that both of the colors in one cell must be either the dark versions or the light versions. There's also a bit for blinking, which swaps between the foreground and background color. And then you can also choose the border color. That's the whole thing. There's no characters or character generation or tiles or anything like that. It's just raw bitmap. When you print text on the screen, it will simply copy the characters from ROM to the bitmap. Audio is, like I said, there's this piezo speaker, and you can make sound by bit banging a single bit on and off. And when you're doing that, it takes 100% of your CPU time. So most games either didn't have any sound at all, or then they had very short chirps. And if you try to make a game that runs at 50 Hz, this is a PAL device, so the full frame rate is 50 Hz, then you want to have sound, then it means that you have to dedicate a significant amount of your frame time to sound. The example that I have on this slide is from Manic Miner that I analyzed, and Manic Miner simply doesn't try to run at 50 Hz. It just does a bunch of things to make things run, and spends certain amount of time to play sounds. The sounds that it makes would take something like 40% of frame time if it was trying to run at 50 Hz. So in Manic Miner, if you have a screen with a lot of moving stuff, the frame rate is lower because it just runs slower. The data storage from typically C-cassette audio is rather slow. The speed is 1023 to 2046 bits per second. It's this range because zeros and ones take different time on the cassette. On average, you have something like 1364 bits per second, which means that loading 32 kilobytes, which is not even the whole memory of the device, would take over 3 minutes. The main input device is the keyboard, which is nicknamed a dead flesh keyboard because it's a rubber sheet on top of a membrane. The membrane itself is a 2-layer one, and the membrane outputs one 8-wire and one 5-wire ribbon cable. The 8x5 matrix can be seen in code directly. Like I said, there's no joystick port, but there's an expansion port, which meant that a lot of different peripherals were made for the 48K spectrum, including a lot of joystick adapters. But since there's no standard, it means that there were several different joystick standards. So typically when you run a ZX Spectrum game, the first thing that you can see is a menu asking if you have a Kempston or a cursor joystick, or if you want to play with a keyboard. Now then, when writing software for the 48K Spectrum, probably the most important thing to understand is the memory map. First you have the 16K of ROM. After the ROM, there's the screen memory for the bitmap, which again is not linear. And then after the bitmap, there's the color data. Then you have a bunch of data related to the BASIC, which is basically the operating system of the device. So if you want to do some ROM calls to print stuff on screen or something like that, you might want to leave these alone. Then there's the available memory, and then a little bit of reserved stuff at the end of the memory, which is the custom graphics for printing the ROM routines. So if you want to have a custom character set, you would put it there. But since we are doing some serious stuff, we are not going to return to BASIC, so all of those reserved things are pretty irrelevant. This memory map was from the URL breakintoprogram.co.uk, which also has a lot of interesting and useful blog posts about the Spectrum programming. Let's say that we are going to make a program that doesn't care about the BASIC at all, so the memory map looks more like this. You have the ROM, you have the screen memory, you have the color data, then you have a bunch of consented memory, and then you have the 32K of fast memory. And this is all the storage you will get. All your executable code, all your data, all your variables, all the buffers you want to use, your stack, everything has to be here. That's probably the biggest limitation of the 48K Spectrum. There was also a 16K Spectrum, which looked exactly the same, except that you didn't get the 32K of fast memory. You had to make your programs run from the 9K or so of free memory, and this is assuming that you don't care about the BASIC. So what else do we need? Interrupts. The Z80 only has a single interrupt, and that occurs at the start of the frame or at retrace. I can't remember if it's the start of the retrace or the end of it, but anyway, once a frame. In order to get there, you simply enable interrupts and then execute a halt instruction, which will then halt the execution until the interrupt happens. Now, the interrupt routine itself by default is in ROM, which is near the start of the address space. And while for some cases it might not matter if the ROM routine is run, it does stuff like scanning the keyboard and stuff like that, so it wastes some CPU time. So you might want to have a custom interrupt routine. The Spectrum has 3 interrupt modes. The one that is in use by default jumps to a fixed address, which again is in the ROM area. Then you have another one that jumps into basically a random address. I think it's based on some external hardware that doesn't exist for the Spectrum. And the third one that can be used, you set the address of a table that contains the jump addresses for the ISR. So if you have some external hardware that says that, okay, I want to have interrupt that does thing A, then you would put that value in some bus, and then when the interrupt occurs, the processor would then look into the table and say that, okay, I need to jump to this address based on this value from the bus, and then you get the interrupt. Now, that input value is basically random, so you need to have a 257 byte table at some fixed address in memory that you can set, but there are some alignment limitations to where it must be. And then you fill it with a single value. So, for example, if you have a table of FD, so that every byte in the table is hex value FD, then when the interrupt occurs, you will get a jump into the address FD. So how do I make programs for the 48 Spectrum? For audio, well, on the 48K Spectrum, the audio is pretty minimal, and I usually use Shiro's Beep Effects library. For graphics, I've made a PC program called Image Spectrumizer, which can be used to make graphics for the Spectrum. Packaging or making the actual binaries that can be distributed, I built a tool called Mackerel for Make a Release. And code itself I generate using SDCC, which basically means doing Z80 assembly. In more detail, since the 48K Spectrum doesn't have an audio chip, it only has the bit-banked piezo speaker, music is largely out of the question. There are some crazy people like Shiro who still do make music for the piezo speaker, but can't really do anything else except for some really minimal animations while music is playing. For the commercial games that had music, you had a main menu or something like that with music, and that was just playing music and waiting for a key press, basically. For the actual gameplay, there's the short chirps that I mentioned earlier, but if you have a non-real-time game, like something where you have moves, then you can have some slightly longer sound effects which might take several frames to play. So for the graphics, I made my own tools out there for this, but I started from a completely different starting point. In my opinion, it's good that you can use whatever drawing program that you like. For example, you can use Photoshop or even Windows Paint with my tools. The tool will detect whenever you save the image to disk and then reload. And in the tool user interface itself, you can add some filters like change the saturation of the images and add some dithering and all sorts of things that, since the Spectrum graphics simply has limitations. For sprite data, which is for all my games is simply just black and white, I have some simpler command line tools which load PNG files and calculate the pre-shifted data that is easier to put on the bitmap, and then outputs those as tables that can be loaded into C programs directly. The 48K applications are distributed as tape images, which can actually be turned into waveforms and loaded on the actual device if you really want to go through that. But typically they are for emulators which load them very rapidly. In order to make the tape images, there are some tools out there, but I made my own, which also adds lots of compression and stuff like that. And the basic idea is that you can use the whole memory space on the Spectrum with my tools. Typically, you have a basic loader that loads a chunk of data into memory and then does a basic instruction that calls the start of the machine code. But this means that you have to have the basic in memory. So what Mackerel does is that it has this loader which then puts itself into display memory in order to leave the whole rest of the memory alone, and then decompresses the loaded data over everything in the memory space, and then jumps to the start of your program. The Mackerel also displays some statistic information about how big your program is and where everything is in the memory space. The SDCC or small device C compiler is the main choice of C compiler for the Z80 at the moment. At least I don't know of anything else that compares. The Z88DK does come with another C compiler, but it generates a different kind of code. The Z80DK also comes with its own version of SDCC. The SDCC generates okay code in that it's very easy for a human to beat the SDCC in optimization. But as long as you have your very critical routines, like let's say sprite drawing or such written in assembler, you can pretty much leave the rest of it as C code. The code is also pretty readable, and I've used it several times as the starting point for optimizations, where I haven't needed to rewrite the whole routine in Z80 assembly, but I could just take the code that SDCC generates and start optimizing from it. One of the bad sides of the SDCC is that the assembler that it uses isn't very great. It also uses a slightly different syntax than other Z80 assemblers, so whenever I've needed to use code by somebody else, I would have to do some conversion by hand. And there's things missing like macros and stuff like that, but it works, I guess. So, why use C? Well, the primary reason to write in C is that it's not assembler. It's generally easier to write C code than assembler code, and faster at least. You don't need to care about stack and stuff like that. And when writing some complex algorithms, like if you want to write a triangle rasterizer or something like that, you might want to first get it working on PC with a debugger, and then port that over to the Spectrum. And this you pretty much can't do if you're writing in assembler directly. Now then, why not write C? Well, the primary reason not to use C is that it's not assembler, because, well, the performance stuff aside, you have a general loss of control. You don't know where your code actually exactly is. Your code size might be all over the place. How much stack you are using. Some routines might benefit having absolute address of code. You can't do stuff like self-modifying code and stuff like that. But as usual, most of your code isn't going to require all the speed all the time. So a mixed C and assembler code base is usually the best way to go. SDCC itself is not just a normal C compiler. It has a lot of extensions for the small devices. Like you can declare a variable and say that, okay, this variable is in this exact memory location. And if you are doing some outputs and inputs to ports, you can declare those in C and then use them as a normal variables, and it just generates the code to do the outs and ins. You can also set the start address, the start of your actual code, and so on using SDCC. Now, the way that I'm using SDCC is that I don't have a standard library. which means that since the Z80 doesn't have a division instruction, there is no division in C or multiplication. There's no memory allocation, no printf. All of those things have to be written from scratch. There is an alternative. You can use Z88DK, which has standard library and it handles all sorts of things for you, but that's kind of a problem for me because I don't want to give up that control. That I kind of want to be in control, but still not so much that I'd write everything in assembly. If you are getting into Spectrum development, do check out Z88DK, but it's just not for me. So, how does this toolchain deal with the memory map? First of all, where's the code? Where do you put the code? If the code needs to be fast, then you probably don't want to put that in the contented memory. Where do you put the stack? Where do you put the data? What data? If the data is not performance critical, like you might actually store some stuff compressed, then you can put that in the contented memory, and when you decompress it, the target buffer might be in the fast memory. All of these things vary from project to project. So, for example, in a real-time game, I would put everything possible in the fast memory. But then when I'm writing a game engine which is not real-time, then I would want to plan things so that I'm using the memory as efficiently as possible and just use as many bytes as I possibly can. But then, since this is C and we don't know exactly how much space everything takes, there's the possibility of overlaps. Like if your stack writes over your code, that's bad. Your stack might write over your data, that's probably also bad. Or your data might write over your stack. That's pretty much the bane of C programming on the Z80. So the tools that I've written, like the Mackerel tool, which shows the memory map, that helps somewhat. If I see that, okay, I only have a few kilobytes where the stack is, and then I have some function that allocates a big buffer in stack or something like that, that's probably a problem. I've also written some scripts that analyze the logs from the linker so that I can see how many bytes each function takes without having to look at the actual assembler listings. So if I need to optimize for space, which eventually always happens on 48K, then these scripts are very useful. If I can see that some function that really shouldn't take that much space is eating a lot of space, then the logs will tell me. So what have I actually released on the 48K Spectrum? I did a bunch of early experiments which were more or less demo effects, but I never really made a demo because I really think that demos should have a soundtrack, and the 48K Spectrum music isn't. Well, it isn't. So then I started looking at making some games. I made a shoot 'em up called Solar Gun, which was pretty much a continuation from the demo effects. It runs at 50 Hz. It has a scroller and some fancy interlacing stuff. Then I participated in a Ludum Dare 48-hour competition and figured out what the heck, I'm going to make a Spectrum game, and well, it's really nothing special. There you go. And the most finished game that I made is called Matheract. I actually got graphics made by somebody who knows how to do graphics. It's a puzzle game where you have to navigate a 3D maze and you only see a 2D slice of it at a time. Then I started making game engines. I made a trivia game engine inspired from thread on the World of Spectrum forums. I found some datasets for trivia questions and made a bunch of trivia games based on this engine. I don't think anyone else has touched the engine, but it has been written so that it's possible to use it without having to code anything. You just add the data and it will output another Qt 48K game. And then I wrote a multiple choice adventure game engine, and this has been used by some other people, I think in Spain. But there's a compiler and all sorts of funny stuff. It supports images, it supports sound effects, it supports custom code if you want to input your own code there. And after making some sample stuff with it, I never really touched it again. But that's one thing that I'm planning to revisit in the future. The 48K storage limitation is actually rather steep when you think about storing text, because text takes surprising amount of space, especially if you include some images. So, after the 48K Spectrum, I did get a 128K Spectrum, the plus 2 model to be exact, and I went through the trouble of fixing it so that it runs and I can get an image and so on, which actually required me to desolder some transistors and swap them around, because apparently they were the wrong way around from the factory. But then I simply didn't do anything with it. Looking at what it would have added, there's a double buffering system, there's the AY sound chip, some additional banked memory, and I think it has a reset button, and the keyboard is not dead flesh, but it's not very good in my opinion. I don't know why I never actually did anything with it. It just felt like it would require a lot of effort to update Mackerel to output 128K stuff, and the additions didn't really feel worth it. The sound chip might be, but the audio output was so noisy from this particular device that I didn't really explore what it would sound like. So it went to my shelf to gather dust, and then a bunch of years went by. So we would have to ask, what next? I had heard of the TB Blue project way before the Spectrum Next Kickstarter in 2017, and everything that I've heard sounded really promising, because most of the retro computing projects back then were just aimed at a minimal implementation that lets you play the old games. Some of them even had reduced keyboards that only had the keys that you need to play games, while the TB Blue was aiming to have a whole hardware implementation that would cover not only the old hardware but also lots of the new clones and also the extensions that would bring it to the future. So when the Kickstarter in 2017 happened, I jumped on it, and while the developer boards did ship in time within a year from the Kickstarter, the cased versions did take their sweet time and only shipped in 2020. So I've only had a few months to play with this, and well, I could have used the time better, but I have a lot of other interests to waste my time on, so I haven't gotten that deep into the next yet. So a little bit of history. The 48K Spectrum was the third ZX computer from Sinclair. Extremely cheap home computers with very limited capabilities. Only after the 48K came out, it had the critical mass of features like a graphics chip that would show the image while something else was going on, for example. I never used the 80 or 81, so I'm probably a bit too critical about those. Since the 48 was a successful machine and a very simple design, it was widely cloned. There were at least 2 lines of official clones, which naturally also added some enhancements, and there were tons and tons of unofficial clones, especially in the former Soviet Union, who couldn't, for historical reasons, really have the Western devices in there. After the 48K Spectrum, there were also official sequels, the 128K versions, which came to be because there was a tax reform in Spain, and they made some weird rule that these hobby computers must be taxed And the limit that they said that okay, anything that has 64K of memory or less, that's a hobby computer. Anything more is a serious machine, and that means that they don't need to be taxed as much. So naturally, the 128K Spectrum came to be. Also because the Spectrum was so limited and had the expansion port, tons and tons of external peripherals and expansions came to be, both from Sinclair and from different companies. So that also expanded the stuff that the Spectrum could do. So the Spectrum Next is basically the best of all worlds, pulling many of the enhancements from all of those clones, as well as lots of the expansions that different people have made. And on top of that, it also has a bunch of its own enhancements. The idea was that what if Sinclair did continue developing the machine further, what would it have looked like? But it's not really only that, because it has a bunch of modern features such as SD card as the input, which naturally wouldn't have existed in 92. It also has a massive amount of memory, which would have been a bit out of place in the 90s, early 90s at least. Now finally let's look at the hardware. The heart of the machine is a Z80, or what it's called Z80N, because it has some additional instructions such as multiplication and a barrel shifter and stuff like that. It also has a bunch of turbo modes, so it can run at maximum 28 MHz. The 28 MHz mode does have some caveats in that some of the instructions take a bit longer than in the slower turbo modes, but it's still way faster than the original machine. The Next has up to 2 megabytes of memory. In practice, I don't think that many people will keep the 1 megabyte that was the standard for the first Kickstarter. I have a machine from the first Kickstarter, and I have added the 1 megabyte extra memory. It's very cheap and easy upgrade. Out of the 2 megabytes, about 1.8 megabytes is directly usable. And then there's the graphics capabilities. In addition to the old ULA graphics mode, there's multiple different modes, 256 color palette modes, there's hardware sprites, layered graphics, so that you have these different modes on screen at the same time with some color saying that okay, this is a see-through color, so you can. The video out is no longer TV. There's a modern VGA, RGB and HDMI output. The timings of these is an interesting topic that I am not going to get into in this presentation, but it is something that you will meet if you start playing with the Next. Basically, original Spectrum was a 50 Hz machine because it's PAL, and modern HDMI is 60 Hz, so there's some interesting stuff going on there. For audio, the speaker interface still exists. You can actually put a piezo speaker into the Next itself if you really want to, but it doesn't ship with one. Instead, the audio comes out from the either HDMI or the dedicated audio out. And then there's 3 AI chips instead of 1 that was in the 128K Spectrum or 2 that was in the Turbosound external peripheral. You can also play samples, but that's a bit more involved as far as I know. I haven't tried that yet. For media access, you can still load from tapes if there's something wrong with you, but there's the SD card, which can load tap files instantly like the emulators would, or you can use the Raspberry Pi accelerator to turn those into WAV files and wait for those 3 minutes or more for your games to load if you really want to. And then there's the WLAN, which is less utilized than you would think, but we'll get to that later on. The keyboard is really nice. There's 2 joystick ports, port for PS mouse, and you can also plug an external PS2 keyboard in it if you want to. And there's the expansion port if there's some really old expansion device that you want to use. As a word of warning, if you have an old Spectrum and you get the next, the power units seem like they work the same, but the polarity is reversed, so if you mix your PSUs you will fry either your old machine or the next. One thing that happened on the way to the Next was the disk operating system, and Spectrum Next has its own version, and this means that you are not alone anymore. You can still take over the whole machine if you want to, but it's usually a good idea to play nice. There's a couple of different kinds of executables. There's so-called dot programs, because you can call them from BASIC by starting with a dot and then writing the command name, which means that the BASIC will run your program and then return back. You can also pass command line parameters and stuff like this. And if you're making a dot program, then suddenly it makes sense to not write over all of the stuff that BASIC cares about, because you are going to return to BASIC. There's also a convenient format, .nex, which is meant for big programmers that take over the whole machine and need a reset to return. You can write a next program that exits cleanly, but if you are really going to try to use everything in the machine, you probably don't need to. Apart from these two formats, all of the old formats still work. You can make tape files. There's a bunch of emulator snapshots that the Next can also load. Now then, the Z80 can only see 64K of memory, but the Next has 2 megabytes, so how do we access those? Naturally, that's done with banking, and there's a lot of historical ways of doing the banking, so it gets a bit messy. The original 128K Spectrum had 16K banks, and you could only bank to the last 16K of the memory space. There's a special all RAM mode that was introduced in order to support CP/M in some version of the Spectrum, and the ROMs also got a bit crowded because you can only have the 16K of ROM visible at the time. There's a bunch of ROM banks, and there's a different banking mechanism to swap between the different ROMs. The Next introduces a very flexible and easy banking system. The whole memory is split into 8 kilobyte pages, and you can swap out any of those and even map everything to the same or whatever you want. But the old mechanisms are still there, and they may override the new mechanism, so you just have to keep that in mind. And why can't we just map the whole 2 megabytes? Well, the 256K that are not available directly are taken by multi-phase RAM, div-MMC RAM, and a bunch of ROM pages. So basically, if you want to access the disk, then don't worry about it, just leave them alone. About 128K of reserved 256K can still be accessed relatively easily, but it's still much more of a hassle than the rest. So, well, this is an 8-bit machine. If you really feel that 1.8 megs isn't enough, you're probably doing something wrong. Now, the 48K Spectrum, like I've said multiple times, was extremely simple. There was just one port that you could use to control all of the features, like reading the keyboard, changing the border color, outputting audio, and so on. Everything in the one port, one 8-bit port. Now, the Next has over 25 ports and about 100 configuration registers. So there's a lot more going on. Of course, you don't need to use everything. You probably won't use everything, especially since there's a lot of historical stuff that you are not going to touch. And everything is still quite manageable, and the documentation is pretty great. And if there's a problem with the documentation, there's a very active Discord where people point out problems with the documentation, and these get fixed pretty quickly. Okay, let's say you don't have hardware and you want to do something for the Next, or you have the Next but still want to develop on your PC instead of working directly with the hardware. You can use emulators. But first of all, there are no perfect emulators, because the Next does a lot of things at the same time, and that doesn't make the emulation easy. Second, because of the previous point, the emulators require a lot of processing power, so you better have a rather high-end PC to run them. Then transferring files to the emulators is not trivial, because the emulators need to emulate the actual drive mechanics instead of ever to emulate. So transferring files to the emulators is not trivial. You need to use some external tools to play with the drive images and stuff like that. All that said, there's two emulators. There's Speccy and Zezarugux, or however you are meant to pronounce that anyway. I use neither, so I can't really say which are better or worse. I'm under the impression that one of them emulates better, the other is faster, but other than that, if you want to look into them, better look into both of them and see which one you like better. Now, ignoring the emulators, the basic cycle of developing on the Spectrum Next is to copy your file on an SD card, eject the SD card, insert the card in the Next, reboot the Next because Next happens to notice that the card has been gone for a while, run your program, eject the SD card, start over again. I actually developed a couple of programs this way, or a couple of test programs, and then figured that there must be a better way. Now, there's some Wi-Fi enabled SD cards on the market, which are surprisingly popular with Next developers, which you can just drag and drop files on your PC to a folder and then they appear on the SD card. But I didn't really want to invest on one of those, and anyway the Next does have the WLAN capability, so why not use that? So I wrote a new tool called NextSync, which can be used to transfer files to the Next. I'm actually surprised nobody did anything like this before, because the development boards have been around for 3 years, and it was pretty obvious to me that something like this has to exist once I got my Next. I wrote a server that's about 300 lines of Python that's running on PC, and then I wrote a .command on the Next, so you can run it from a basic script if you want to, for example. After this, you build your program on the PC, have it copied to the folder that the sync is looking at, run .sync on the Next, and then you can just run your program and repeat. It's much more convenient than swapping the SD card around. So let's look a bit more at the .commands. The .commands are kind of like good old MS-DOS.com files, which are all code. There's no header. They are executed from a specific address. But while the .com files on PC were about 64K, the maximum length of a .dot file is 8K. You can extend that 8K with some work by allocating more memory blocks, loading your code from disk to those blocks and so on. But it's a bit of a hassle. If you can keep it to 8K, things are pretty easy. Other commands can access the operating system, so you can load files, save files, allocate memory, whatever. So they are very handy for small tools, and the Next ships with a bunch of commands already. Now, the Next programs, like I said, are meant for big programs, and they don't need to return to basic. The Next loader itself is a dot program, which configures the Next to a more or less known state. There are some configuration registers that you still should always set yourself, like the location of the layer 2 graphics. And then it loads the program into memory. Nothing stops programs still from loading more stuff off disk, as long as you haven't messed up the operating system by, for example, writing over it in memory. There are some banks that you should leave alone if you want to use the operating system. The memory map and planning where you put your stuff still matters. If you need the operating system, then you should keep the ROM around and also keep those few banks around the operating system. Depends on. The ROM itself can be mapped in and out as needed. Now, you need to figure out where you are going to put your code, where you're going to put your stack. If you're swapping data in and out, well, that's pretty simple. You just say that, okay, this bank is always for data, I can swap in and out, whatever, but if you're swapping out code, you probably want the code that does the swapping to stay in memory and not swap under it. And of course, if you are swapping out your stack, that's a bit dangerous, but it's possible. The good news is that there's no contented memory anymore, but on the other hand, there are some memory banks that are special. The development wiki has a handy list of things that you should keep in mind, like the ULA memory, for example, has to be in special place because of the required timing. The graphics itself is rather interesting pile of things. There's a background color. If all the layers are invisible, you can define what the background color is. The ULA screen is still a thing, and there's extended versions of those from the Timex clones. There's ULA Plus, there's ULA Next for some more highly controlled color stuff and stuff like that. There's a low-res mode that's 128 by 96 pixels, which is really low resolution, but then again you have very limited processing power, so if you are going to do some so-called shader graphics kind of stuff, it's probably something to look into. And it's also linear, unlike the ULA, so it's much more handy. There's a sprite layer. You can also alter which layer is in which position, so you can put the sprites on top of the graphics or under them, for example. Then there's the so-called layer 2, which is primarily 256 by 192 pixels, which is the same resolution as the ULA, but you have one byte per pixel. But there's other resolutions too, 320 by 256, which is interesting in a memory layout point of view, and 640 by 256, and 16 colors for some really high resolution graphics. There's also a tile map layer, which is basically a text mode, but all of the 8x8 characters can have 16 colors each. Many of these layers have a separate palette, so you can have either completely different kinds of colors for different layers that can be seen through, or you can do palette tricks on separate layers with their separate palettes. There are some limitations to how you mix these. For example, the ULA layer shares some stuff with the tile map layer and the low resolution layer. There are some limits, but there's a lot of things that can be done with all of this. So let's look at the layer 2 graphics. The resolution is the 256 by 192. You could say that's the mode 13H or next. Mode 13H was the MS-DOS VGA resolution of 320 by 200, which was just turn it on and start plotting pixels. Now, that's 48 kilobytes of data, and we only see 64K at a time, so you basically have to swap banks. Or if you want to, you can just swap out the ROM, map the 48K to the top 48K and just run your programming at the bottom 16K. That's entirely possible too. Each 8K bank is 32 lines. The 320 by 256 mode is actually rotated so that the rows and columns are swapped, so it's like sideways in memory, but it takes 64K, so you will definitely need to swap things in and out. Talking of palette, the color selection is 256 colors out of 512. So the color space is 8 colors by 8 colors by 8 colors, which also means that there's only 8 pure shades of gray. The good side is that all of the good old palette tricks are back, so you can have very cheap fade-ins, fade-outs, desaturation stuff. You can have palette cycling, so if you want your water to ripple without plotting any pixels, that's very easy. Or you can do cross-fading between two 16-color images very easily, or 8 and 32. All those things are usable. And remembering that different layers have their own palette, you can mix and match all of these tricks with several layers. The interrupt stuff, all of the old stuff still works, so you can still create your jump table and all of that stuff. But since the default interrupt routine points at ROM, and you can get rid of the ROM, there's a much easier way to handle the interrupts now. You just swap out the ROM, put in your code in the first memory bank, and it just gets called. The interrupt line can also be changed very easily. There's one next register that just says that, okay, this is a scan line that triggers the interrupt. And if you want an interrupt to happen on a different rate than once per display refresh, that's also possible by changing the interrupt line on every interrupt. In addition to all of this, there's a lot of other things that can be used for hardware trickery. There's a copper, which is an idea taken from the Amiga, which is a very simple core processor that executes on every scan line. You can do the tricks with the different graphics layers. The graphics layers themselves have different offset registers. You can change the memory offset from where the layers read their graphics. You can play with clip regions and stuff like that. And even though the original ULA layer is pretty crappy, it's still there, so it might be useful for something. Now then, my Spectrum Next toolchain doesn't really exist yet. There's a lot of holes in my development toolkit, but it's getting there slowly. I'm still using SDCC for programming. There's a bunch of open questions with that, like what if the programs get bigger than 16 kilobytes or bigger than 32 kilobytes? What will they do? I can make code overlays that are basically separate programs that get compiled and then loaded to specific positions in memory and then called, for example. But that's something that I'll deal with when I get there. Converting the graphics should be pretty much easier this time because everything is 8-bit palette stuff, and even though the color depth is very limited, it's still far cry from the problems with the ULA graphics mode. As for audio, I can currently play register dumps made for the sound chips, but that's not a really lasting solution. So in the very long run, something like a VST that simulates the sound chips and then making some kind of a converter that takes in MIDI files and the VST's configuration and then generates some player code. That might be something that works in the long run. There are some trackers and stuff like that for the AY chips already. As for the final packaging and making releases, some kind of a mackerel kind of solution would be nice, especially if it helps with a memory map and finds problems before executing. The next thing was a big puzzle piece because it makes development on the device much more enjoyable. And if I find some other pieces that require those programs, that's probably what I will do. Finally, I'll leave you with a huge list of links for all the source code that I've done, all the tools that I've done, and all those links to various communities and tools that I'm using. So that's where I am with my Spectrum journey. I hope this has been, if not entertaining, at least useful. Thanks for listening. If you have any questions, feel free to contact me. Bye!
Okay, I guess I'll leave these links here hanging. I'm going to try to call in Yari to see if we can get him to answer a few questions regarding the presentation. It's a really cool seminar. I really enjoyed it. Hello, Yari. Are you there? Can you hear me?
I can hear you.
Okay, good. Please mute the stream so there's no echo. Okay, thank you so much for that presentation. It was really cool.
Yeah, thanks.
Okay, so let's get right into some questions that I have been lining up for you here. The first question, I was thinking, how big was the ZX Spectrum available in Finland? Because most Finnish people I talk with, they only seem to have had the C64 or the Amiga. I don't really see that many people with Spectrum. So can you tell us a little bit more about the history of Spectrum in Finland?
Well, I think it was kind of like 50-50 that people had either the Spectrum or the Commodore 64. I don't really recall which was more popular. I think eventually the Commodore 64 was more popular because it had the better games.
Mm-hmm.
But while I was in school, I do remember that several other kids also had a Spectrum.
Yeah. At some point in your presentation, you were talking about the ISR that was jumping around in different places in memory due to a hardware oddity. Was it? Can you tell us a little bit more about that oddity? If you know, is like specific. Every time you run, it jumps to a different place, or it depends on the model, or
Uh, well, if I remember correctly, and I will probably be corrected, uh, the Z80 CPU has 3 different interrupt modes, and ignoring the one that is really unusable, the default one just jumps into the ROM area, so that can't really be used for software use. But then there's another one that's meant to be used with some external peripherals, some other chips on the computer, which will say to the Z80 that, okay, now I want you to interrupt and do this specific thing. So the Z80 gets the interrupt from the outside and reads some data bus saying that, okay, now I should do the interrupt with the value whatever, like value 15, for example. And then it would read from memory that, okay, number 15 means I need to jump to this specific address. So that's the mechanism that is abused to make the software interrupts. And since we don't know what value will come from the bus, we will have to assume that it can be any value.
okay.
And that's the thing that requires the 257 byte table.
Yeah, it feels like a bit of a waste of space when you have to be so careful with space. But okay, fair
Once
enough.
the table has to be in some specific place in the memory, so
Hmm.
doing that with C is a bit tricky.
What happens if you send it to like to memory that doesn't exist? Like, do you get a memory overflow error? Like if it's beyond the 48K?
Well, 64K and memory wraps around, so
Oh, it wraps around. Okay.
there is a
Okay.
trick. There is a trick because the Sinclair was subcontracting parts of the ROM, and I think it was some printer drivers or something like that that never arrived. So part of the ROM is actually filled with just FFFFFFF. So
Oh.
you can put the interrupt table there, and then every time the interrupt occurs, it will jump to the last byte of the whole memory area. So if you put a ret there, then you just have disabled the interrupt handler. Or you can put some other opcode there and then just trust that when the memory uh, wraps around that you get an instruction that jumps to somewhere that you put your code in.
But PED7G is saying on the chat that the high 8 bits are coming from register in CD80, the low bits from the data bus, and data bus is random in case of no peripheral. So that's what you were saying. Can we fake that there's a peripheral in by code somehow? I guess you can't. It goes check the hardware directly. That would be a nice way to bypass that. Anyways, we're talking nerdy cliche stuff. Let's go on to the next question. Why people are asking if you're gonna put the presentation on your website? I think you have
Oh, it's on
already.
YouTube. It's on YouTube.
Okay,
I will
well,
probably post a blog post eventually.
okay. Why did you do your own image converter when there were quite a few out there already? Were you like learning the machine and just wanted to learn a bit more of the format, or you just wanted more control over the images?
Well, why is any one of us playing with this ancient hardware?
Too much free
Of course,
time.
I really like to reinvent the wheel a lot, and the other tools that are out there start from the position of limiting the artist rather than doing the conversion. And it probably leads into more optimal solution to limit the artist and say that, okay, you can't put a red pixel here, while my solution is to, well, do whatever, and then we'll see in the conversion if we can get into something usable.
I remember since you were also a member of our the person who started organizing the text mode demo compo, I guess you like converting between formats because you did a lot of work converting between pixels and characters.
Well, I suppose.
Did you ever consider doing a text mode demo for Spectrum? I know the car set on Spectrum is not that interesting or as interesting as, for example, the C64 with all the patchy stuff, but did you consider it?
No, not really. The Next does have the tile mode, which could be used to fake text mode, but I don't really see the point.
Okay. Fair enough. I had a question here about the C compiler and machine language. Oh yeah, because a lot of the people that I talk with who do Spectrum demos, they usually say that they just do directly machine language stuff. They just learn the opcodes and they do it directly. Maybe they do some assembler and go from assembler Z80 assembler. But you seem to prefer the C compiler version. I heard you got a lot of hate because of that. Can you talk us through your reasoning why C compiler and not pure assembler or
Speed,
pure machine language?
speed, basically. I value my time more than anything in this. Well, I did write a game for a 48-hour competition, for example, and I really didn't use the 48 hours. I probably made the game in something like 6 hours, and that's basically because I had the toolchain on. I wrote the whole game in C using the assembler optimized sprite routines that I had already made.
And you
So-
think you wouldn't have had time if you had made everything directly in Z80? Because in Z80 you end up reusing a lot of chunks. You end up doing like this part does,
Well,
send something.
that's true, of course, but it's
Not
just
your
my choice.
yeah, not your style of coding. There are also some people who have been working on a basic compiler, so you write in basic and it transforms into machine language code that's not horribly slow like it is on the original 48K and 128K. Do you know something about that? Do you want to talk a little bit about
Well,
that?
I've heard of the Boreal compiler, yes. Seems interesting, but it's also not.
You rather use C than use basic.
Yeah.
Yeah, pretty much. Someone asked, what is the next game that you are working on, and where is the screenshot of it?
Well, the screenshot doesn't exist yet because the game doesn't exist yet.
Ah,
I have some projects that I work on while I'm exploring the next and what I can do with it. And the idea that I have is like a perspective shoot 'em up kind of thing that fakes a lot of things, but we will see if that ever becomes anything.
okay. Fair enough. You were talking about
But
sound.
it helps to have some kind of a target to work towards while you're doing these kinds of things, while building the base technology that whatever I will eventually end up doing will use.
So another Ludum there.
Probably not.
Another demo party with a game compo. Maybe it would be awesome if you could win assembly game compo with a game made for Spectrum.
Yeah, that would be interesting considering that, well, the last time that I entered the game competition in assembly, it was more of a funny video competition. The games didn't really matter, but
Yeah, there's this weird thing on assembly. It's more like trailers of games than actually. I don't see like some of those videos. I didn't see any gameplay. Like, what the hell am I voting on? Where's the game? Which is
Yeah.
weird. But I guess like the games are pre-released, so you can download them and play them yourself, and they're just showing the trailer. It's weird. I didn't really get it. Whenever I saw that part of the compo of assembly, I always found it weird. But well. Moving on, you talked a little bit about getting sound working into your framework. I remember some people mentioned that you can just use Vortex Tracker and just outputs this format. I think it's PT2 or PT3, and that it's relatively easy just to get to play. Did you ever look into that, or?
well, I think I said in the presentation that there are trackers that exist, but I don't know.
And but were you aiming already at the next or at 128K? Because I guess with the next having three chips available, you can do some more interesting stuff. And I'm not sure if there are trackers who use those three chips. I guess there are. I mean, if people have been
There,
using.
there is a next specific tracker.
Nice.
Can't remember what the name was, but it was something obvious.
I need to try something with that. I mean, I have a
Next,
next,
next have
so
like a digital audio workstation.
yeah.
That
I need to try that. Try to do some music, make some noise on the Spectrum, make noise
but
again.
but I think that there's something bigger that could be done. Like if somebody, not necessarily me, makes a VST that emulates the three sound chips, you could make some instruments that a single instrument that uses like 6 channels or something like that, for example.
But if you're using a VST, then you have to put it like into a DAW of some sort and then export the format like into Renoise or something
yeah,
like that.
yeah, and then you save it as a MIDI file and then you use a converter to make it into a format that can be played on the actual hardware.
I feel like a tracker would be easier, but that's just me. Emok is saying on the chat that NextDAW is the name of the thing. Okay, last question I have for here. In your opinion, why is the Amiga the best computer ever made?
Well, I worked with RG Michael for a couple of years, and he was a cool guy.
So that explains everything. So, anyways, jokes aside of what the best machine is. Thank you so much for this presentation, Yari. Was great to hear. I really learned a few things more about the ZX Spectrum. I had two of them, but I only coded it in BASIC for them, so I'm still like finding the inspiration. I need that how hard can it be moment to get my hands dirty and try some stuff into it. So it was great to hear about your struggles and the ways that you found around things. So thank you very much for that.
Thanks for having me.
Is there anything else you would like to add, like something that you thought was missing from the presentation, or any
No,
last
not really,
words?
but people can contact me and ask more questions if they.
Any advice for anyone who is starting to do stuff on the Spectrum these days? Best place to start?
Well, since the Nexts can't really be bought in retail stores, the easiest way would be probably to get some 48K emulator and just try to get something running there.
Okay. Any books, any references like that, or just read the manual?
Well, the web is pretty full of information regarding programming for the Spectrum. The world of Spectrum, for example, there's a lot of stuff there, and if you get to the next has a lot of documentation that is very nice. So
It was a really cool thing that the Next came with such a big fat manual, like in the old days. Because I remember I learned programming computers by reading the manual of my 128K. So it was really cool to see like a big fat manual coming with the Next, and that you could actually see all the stuff. If you're a new person or if you're an experienced person, you have all the references there for all the stuff on how to use the machine. That was really cool to have. They
well,
don't really do that
that
anymore.
is the thing. That is the thing about the original Spectrum, that you really had to learn some programming in order to do anything like play those games.
At least
You had to.
load asterisk load what's it called, quotes, load quotes. At least that you would need it to know.
Yeah.
Okay, so that's it for this part of the seminar. Thank you so much, Yari, for being here with us for the seminar and for this Q&A session. We're going to continue playing some more demos from Forever Demoparty, so stay tuned for that. I'm going to tune off Yari, so bye-bye, Yari. See you next time.
Bye-bye.
Okay, let's move on to more demos from Forever Demoparty. Let's try to remove this. It was a really cool seminar. I really enjoyed that. I feel bad. I've been trying to get into ZX Spectrum coding for so long now, and I still haven't quite found the right timing to do it. There's always something else that is more interesting. I still have that urge, I did achieve that thing of doing a demo for the ZX Spectrum by collaborating with Elf, but it feels like it wasn't my demo. I didn't program it, I didn't I only had a spiritual say in it. So yeah, I should really try to do some more stuff for the Spectrum again. Anyways, let's play some demos. Let's start with The Path, which is a huge, very long demo. And if you still have patience for more demos after that, we'll see about that afterwards. This is by Cyberpunk's Unity, and it was released in Forever 2004. I think it won the demo compo. This capture isn't that good. I wish I could play this in 50 Hz without the encoding fucking up everything. Actually got third place at the compo in 2004.